Hey, this is Mr. Aiden, and this is AP Physics C, that's Calculus Mechanics, and we're going to take a look at Unit 0, which is the background skills. We're going to do Part 1 today, which is vectors and scalars, dot products, cross products, and graphing, kind of a quick overview of the background skills you will need for AP Physics Calculus. Now, something we're going to hit all year is scalar and vector quantities. Okay, scalar quantities, as you've learned before, is when we're talking about our magnitude only. Our magnitude only. And what does magnitude mean? It just means the number, the magnitude, how big that is, which means we do not need a direction. This is mass, time, distance, speed. You'll often see it in distance and speed, as well as work, these are all scalar quantities. But vector quantities deals with a number, or the magnitude, and the direction, which means direction is very, very, very important for vector quantities. And we're talking about displacement, velocity, acceleration, force, momentum, and these directions can be positive, they can be negative, they can be at angles, they can be many different things. Now, if you can see, I have a vector here, which is called vector A. Hopefully you can see vector A has an x component and has a y component. Okay, you can see the x component is moving to the right, the y component is moving up. Okay, now I'm going to just erase that real quick and take a look at also this vector B. This vector B has a y component that's going down, or in the negative direction, the x component which is moving to the right. So if I happen to add vector A and vector B, hopefully you can see how I can add them tail to tip in order to get a resultant vector. Okay, and I'm going to do that resultant vector in red. That's going to be from the start to the finish, and I'm going to call that vector A. I'll call that vector AB, or actually I'll call that more apropos vector A plus B, because I'm adding those two vectors together. Now I hope you can see vector A's x component, which was moving to the right, and vector B's x component, which is moving to the right, added together, which made your resultant in red going way to the right. But you can see vectors A, the y component which was going up, and B's y component which is going down, cancel each other out. And so if we wanted to subtract these two vectors, let's say we took A minus B, you would simply flip the direction of B and add them in the same way. All right. So let's first take a look at vector notation. Okay. Let's say I have a vector, and I'm going to give you some notation of 4, 3. Okay. That means that 4 is in the x direction, that 3 is in the y direction. We can also call this 4i hat and 3j hat. Okay, which means the same thing. 4 is in the x, 3 is in the y, which means we're going to be going 4 units in the x, we're going to be doing 3 units in the y, which means we have a resultant vector right here, okay, because it's made up of those components. Now, how do we figure out the length or the magnitude of that blue vector, that resultant vector? And I'm going to call that vector V right here. Well, I'm going to use the Pythagorean theorem. I'm going to do 4 squared and 3 squared equals this V squared, which ends up being 5 if you do the Pythagorean theorem for that. Now, hopefully you can see this is at an angle, which means this vector 5, that resultant vector, is at an angle, which means it has components x and y. So how do we figure out what that x and y is? Well, I would just do r, or that vector v, that 5 cosine of my angle to find my x. I would do r sine of theta in order to find the y component of that. Now, vectors don't just have to be in 2 dimensions. We can also have vectors in 3 dimensions. We could have a vector of 4, 3, 1, which means 4 in the x, 3 in the y. Hopefully you can see the y went back into the board like that, and 1 going up, that up in the z direction, which means our resultant is not just in 2 dimensions, our resultant vector is in 3 dimensions. Okay, so we have some vector notation there. Now there's 2 ways to multiply vectors. We just took a look before about adding or subtracting vectors, but we can multiply those vectors. And there's two ways to multiply vectors. One is dot product, and one is using the cross product. The dot product is very important because this is what we use for work, because the dot product gives us a scalar result. And as we know, work is a scalar quantity, which means we're going to multiply the portions of the two vectors that point in the same direction. What is a dot product? A dot product is we're looking at the things that are in the same direction, which means the result is the component of vector A in the direction of vector B. So let me give you an example of this. Okay, a dot product is a very easy formula, and you're going to see this throughout physics. Is our dot product is going to be, let's say we have vector A and we want to multiply it, dot product of vector B, like we would in terms of work. We're going to be doing AB cosine of theta. And so we're only going to look at the things that are in the same direction. Okay, so let's say we're going to take this vector component A and we're going to dot product it, multiply it by vector component B. What we're going to do is we're just going to look at just what's going in the same direction. So the x component of A is equal to 1. The B's x component is 3, so I multiply those two together. When we take a look at the y direction, the A's y direction is 2, the B's y direction is 2, and we're going to multiply those together. And our A's z direction is 3, our B's z direction is 1, and I'm going to multiply those together. And so you can see we have 3 times 1, 2 times 2, and we have 3 times 1. We add that up, and it's 10. It's a scalar product. We only looked at the things that were similar in this dot product, which means the dot product of any perpendicular vectors is going to be 0, because they have, if a perpendicular vectors has nothing in common. They don't have any x, they don't have any y, they don't have any z's in common. But there's another way to multiply, and that is using the cross product. And of course, if the dot product gives you a scalar result, then the cross product would give you a vector result. And we're not looking at things that are similar here, we're looking at things that are different. Okay, and so we have a nice easy equation for cross products. Cross products are way more difficult to do. And we're going to utilize our calculator for those kinds of things. So we're going to, let's say we take the cross product between vector A and vector B. That's going to be equal to AB, you guessed it, sine of theta. Okay, let's take a look at this example. You can see vector A has 0 in the x, 2 in the y, 0 in the z. B has 2 in the x, 0 in the y, and 0 in the z. Can you guess what? They don't have anything that is different, do they? All right. And so when if we would do this on our calculators, we would find out that our cross product of this example would be equal to 0 using matrices here. All right. We have one last thing that we're going to go over, and that is graphing and relationships. Hopefully you don't have relationship problems, but if you do, we can linearize it very easily. You can see this first graph right here. This is a linear graph. Okay, this is a directly proportional relationship here. A linear graph, which means I can find the slope, the rise over the run, or as we're going to see in the next video, the derivative of this. You can see in this next graph, this is a squared graph. This is a squared graph. Hopefully you can see that the data is being squared, which means if we wanted to linearize this to make our data straight, or to take a look at the equation, we would do y equals k, that k is our constant, times x squared. So we would square all your x data, keep all your y data, and it would make this graph linear. Okay? This graph on the bottom here, you can see the bottom middle, this is a square root graph. This is a square root graph. Okay? A square root graph. Which means that our data is being square rooted. Which means if you graph this, y equals k times the square root of x, we would end up, if you graphed your data with those two things, so you would square root all the x values, keep all the y values, it would make a linear graph. Okay. Hopefully you can see these two graphs on the right hand side, they look very similar, don't they? They both look as inverse graphs. This guy right here is in fact an inverse graph, which means we would have y equals k times 1 over x. We would do the inverse of all of our x data. This one right here is an inverse squared relationship, which means y equals k times 1 over x squared. We're going to see those relationships as well. So these are the 5 relationships that we're going to see all year long. One is linear, one is a squared relationship, one is a square root, one is an inverse, and one is an inverse squared. And this is how we would graph this data in order to linearize each one of these graphs. So hope that was good, and I'll talk to you soon. This is Mr. Ayton signing off.